Hi, Syed.
Hello,
How are you doing?
I'm good. How are you?
Not too bad. Okay, I'm gonna disable the waiting room. So,
Okay.
okay. That's odd. Did it work? Oh, that's funny. The waiting room is off, but the people still need to be admitted for some reason.
They seem to be trickling in one at a time.
That's strange.
Oh, there we go.
It's probably because it provides them an option to join.
Maybe.
Hi, everyone. It's cold, very cold. Okay, let's start with some questions before we do some new stuff. We have uh, next Tuesday and next Thursday. So there are 3 remaining lectures. Right, the last day of classes is next Thursday. Okay. Questions? Comments? Everyone is just being quiet. Fine. Okay, so I just wanted to make a couple of comments about assignment 11. Okay, so the first question is a kind of interesting approach to differential equations. So let me just explain why the first question is interesting. Okay, so if you have functions in one variable, okay, but let's say that you consider only algebraic functions, what are often called algebraic functions, and algebraic functions they're kind of more constrained than all functions that you learned. In fact, they're usually taken to be just polynomial functions. So that's why I start with polynomials over a field. And as we know, polynomials over a field is not the same thing really as functions, right? Because you can evaluate polynomials, but so polynomials determine functions, but you could have potentially, depending on the field, you could have two polynomials that determine the same function, even though the polynomials are different. So anyway, polynomials are kind of they're like an algebraic model for functions, but they're not exactly the same thing as functions. Anyway, so if you have this algebraic version of functions, these polynomials, then you can define a differentiation operator, d. And here what I do in these three lines, oh, no, doesn't want. In these three lines, I give a definition of the derivative, which doesn't require you to know anything about differentiation of functions. It's just it's a linear map on the vector space of polynomials, which if you apply it to the constant polynomial 1, you get 0, because we know that the derivative of 1, or the derivative of any constant function, should be 0. And then the derivative of the x function should be 1. And so that's all you do. You specify these two values, okay? And then the derivative is uniquely determined as long as you require that it satisfies the product rule, which is usually called the Leibniz rule. So anytime you have a linear map on polynomials which satisfies the Leibniz rule, basically it has to be the differentiation operator. We just have to make sure that we normalize it correctly so that d of 1 is 0 and d of x is 1. So this is it's a purely algebraic way of defining the derivative, and you only define it on polynomials. Is that clear? Any questions about that first part? There must be at least one question. It's literally impossible that all of you understand what I just said.
Do we need to define any analog to the quotient rule as well?
Sorry, who asked that? I can't see.
N-E-I-L, Neil.
Dion.
N-E-I, like Neil Armstrong, Neil.
Oh, but how come you're not showing up? You're not showing up at all.
Oh, really? Interesting.
For some reason.
We do not have a video, but I am still here. So.
Oh, Neil Gupta. There, I see you now. I mean, I see your square, but I don't see you. Anyway.
Oh, yeah. Out of the camera.
What did you say? Do we need to do what? We need to define.
I guess I was thinking at first, do we need to define some sort of quotient rule? Because derivatives have that. But now I guess I was also thinking
quotient rule. What is that? What is a quotient rule? You mean d of f over g?
Correct.
Well, no, but you don't even have quotients of polynomials.
Yeah. Okay.
And plus, yeah. So I'm not sure. Quotient rule is not really a thing, but anyway, this one is. This is the Leibniz rule. This one's fundamental because you use it to define the derivative in the first place. Okay, so right now, the first question is asking you to find all the eigenvalues and eigenvectors. Now, if we look at this this simple equation, this equation df equals f, it's basically saying find a function whose derivative is equal to itself. And so you could look at it in two ways. You could look at it as a linear as an equation in linear algebra. So this looks like a linear operator applied to a vector equals a multiple of the vector. So this is an eigenvector equation. So in other words, looking for f such that df equals f means that you're trying to find an eigenvector for d with eigenvalue 1. That's one way to look at this differential equation. Okay. Another way of looking at it is the way that you do it in your ODE class, which is you're trying to find a function whose first derivative is equal to itself. Okay, now this is literally the first differential equation that you should probably learn how to solve in your ODE class. And the solution is, anyone?
E to the x.
The exponential function.
E to the power x.
0.
Okay, so we have a bunch of people repeating the same thing.
It's a e to the x plus b times e to the negative x.
E to the minus x, you think? If I differentiate e to the minus x, what do I get?
Oh, no.
Negative e to the.
What do I get? I asked you. What do you get if you differentiate e to the minus x?
Negative b times e.
Minus e to the power minus x.
Okay, and so what does that mean about an eigenvector? What kind of an eigen equation is that?
Eigenvalue.
df equals negative
Lambda
x.
is -1.
Yeah, correct. So that means that e to the x is an eigenvector with eigenvalue 1, and e to the minus x is an eigenvector with eigenvalue -1, right? So the exponent will affect the eigenvalue. The exponent of the exponential, e to the ax, a, the number a, that is an eigenvalue. Okay. Okay, so e to the x. Okay, so, but the thing is that e to the x is not an algebraic function because it is not a polynomial.
Would it be its Taylor series expansion?
0. But can 0 be an eigenvector?
So 0 is a solution to the differential equation because it's a linear differential equation. However, as we know, 0 is not an eigenvector. You know, calling 0 an eigenvector with eigenvalue 0. I mean, what is it really eigenvalue 0? What if I said that it's eigenvalue 150? It's still the case. D applied to 0 is 150 times 0. So it's not useful to think of 0 as being an eigenvector of anything. Eigenvector is, it's important that the eigenvector is non-zero. The eigenvalue can be 0. That's fine, but yeah. So anyway, yes. So the point is that if you expand the exponential in Taylor series, you will always get a remainder term, right? So you will not find a polynomial that is equal to the exponential. That is, well, you can think about that. It can sometimes work, but anyway, the exponential function has a Taylor series expansion which never terminates. So it is not a polynomial, and so that means that you could say that this differential equation does not have any solutions except 0 if you consider only algebraic functions, right? So if you were, you know, if you were a very conservative mathematician who only believed in algebraic functions and didn't believe in this nonsense about convergent series, right? And they only believed in finite math, so you were only allowed using polynomials which have finitely many terms, right? If you were that kind of person, you would say that the only solution to this differential equation is 0. Okay, so then we're in this situation where, which is very similar to the complex numbers, where we say, can you solve the equation x squared is equal to -1? And over the real numbers, we cannot do that. There is no real number whose square is -1. So what we do is that we formally adjoin an extra object, which we call I, and that extra object is not in the real line, right? And we include that object into our number system. And as a result of including I, we also have to include 3 times I, 5 times I, 6 times I, plus 5. We need to add all of the operations applied to that new element, and we need to generate all of the complex numbers, right? So this is kind of like, this is, in a way, it's like the fundamental idea of what's called Galois theory, where you cannot solve an equation with your existing number system. And so then you need to understand, what do I need to add to my number system so that I do have a solution to this system or to this equation? So similarly here, if I don't have enough algebraic functions to actually solve this eigenvector problem, what I could do is just introduce a solution and call it E. Whatever that, whatever it is, I just treat it as an indeterminate, as a kind of formal thing like I. Okay. And what do we know about E? Well, nothing in principle, except that we want it to satisfy this equation. So, okay, so we have a problem. We have an original system of functions, an original a vector space of functions, f of x. We have an operator on it. We have an eigenvector equation, df equals f. It has no solution except 0. Okay, so then we introduce a new object in the vector space. We formally add an extra vector to the vector space, which was not there before. And then, what we need to do is we need to add all linear combinations, which include that vector. And because I want this to be a space of functions, so I want it to have a multiplication, I also add all powers of that vector. So in the end, I end up with this, f of xe, polynomials in 2 variables. The first variable is x, the original variable, and the new variable is this e, which is, we're thinking of it as a new function, right? And that we've added to our algebraic functions. Okay, so now I've enlarged my vector space to polynomials in 2 variables, but my original operator was only defined on u. It was only defined on polynomials in 1 variable. So now if I want to like complete the train of thought, I need to extend my operator so that it's acting on the larger space. So I need to say, okay, fine, I know how D acts on X, and I know how it acts on f of X, but I need to tell how it acts on E. And that's where we just impose this condition. We just say that D is extended to this larger vector space by defining its value on E to be just E itself. And then, of course, in this new vector space, I will have a solution to the eigenvector equation. You see what I mean when I say that it's like the complex numbers. We have no solution to the differential equation. We add it in, and then we extend the differential equation so that it makes sense on this larger ring. Okay, and then I ask you to find the eigenvalues, eigenvectors, and generalized eigenvectors for this extended operator. So this is how like a pure algebraist would study differential equations. They would not, they would not consider C infinity functions and take limits and so on, and define derivatives like that. That involves analysis, norms and such. And so this is a way of approaching it which doesn't use that. So any questions about this question? I just wanted to indicate what I'm really talking about here.
Yeah, I have a question in part 3, question 1. So
Yes.
yeah, that's asking, like the last part says, find a
Okay,
basis
so
for
I'm
S.
going to stop you right now. Just, I don't want you to be giving hints at all.
Oh, I'm just, okay. I wanted to
So I
just
don't
ask
want you to ask, for example, can I do this? Or can I do this following procedure? No, none of
no,
that.
I was going, I wasn't going to ask that.
Okay.
Yeah, so it says put D into Jordan form, but I may be wrong, but then the vector space V, that's infinite dimensional, right?
Yes.
So the Jordan form is a matrix. I don't quite understand. I mean, the Jordan form is basically a matrix, right?
Yes. Yes.
So I don't quite understand how could you.
Yeah, you need to look at the statement of the question. This is a sentence which answers your question.
Okay, thank you.
So that's a good question. The vector space V is infinite dimensional, but this question avoids that problem. Okay. All right, let's get into the material for today. Okay. So I want to talk about volumes and the determinant. Okay. So okay, if we have a vector space, okay, and if I give you, let's say it has dimension 2, and suppose that I give you 2 vectors, let's say A and B. Okay, now A and B, they're linearly independent, as you can see. And from A and B, I can create a parallelogram. Yes. So this is just V, A and B in V, and the dimension of V over R, let's say, is equal to 2. So we have a parallelogram and okay, so my first question to you is, what is the area of this parallelogram? Anyone? Does anyone have a suggestion?
Yeah, Diva?
I believe it would be the vertical component of B minus the vertical component of A times the horizontal component of A minus the horizontal component of B.
What is a horizontal component?
Like, well, this is over 2 dimensions. Sorry, I guess let me be a bit more general. It's relative to whatever basis that we are in, the 2 basis vectors.
Basis? What basis? What basis?
Any basis, I guess. Well, we're over R.
Okay, so then what? So then I'll call the basis A and B.
0,
So
1.
I you said any basis, so I'm picking the basis A and B.
Okay.
So then continue with your explanation. So now I have my basis.
So we want to multiply together the difference of each basis vector for the two respective vectors making our parallelogram.
I don't know what that means, but it's okay. Just do it. So the basis vectors are A and B. So then what's the area of the parallelogram?
Is it just... Okay, I'm drawing a blank. I think maybe I should...
Okay, but okay. So anyone else?
Wait, if our basis is AB, then it's A times B. Sorry, is that the...
Sorry, what is A times B? How do I multiply two basis elements?
Dot B.
What is dot?
Okay, yes, then I will defer to someone else.
Okay, so that's good. You tried hard and failed. That's okay. Anyone else?
Andy, do you have a suggestion?
So we first need like a notion of length. So we take AB with respect to...
There is no notion of length.
So we take AB to be respect to the standard basis, 1,
There's
0.
no standard basis. There's no standard basis. What's standard basis? We're in a vector space of dimension 2. There's no basis.
Oh, you didn't say R squared. Okay.
How come this is so difficult for everyone? I'm just asking for the area of a two-dimensional parallelogram, and we're already stuck.
A times B times the sine of the angle.
A is a vector. How do I multiply A times B? Sorry?
Take the norm of the vector.
Length of the vector.
There is no norm. We don't have norms yet. V is just a vector space. There is no norm on a vector space.
Can we say the cross product of A and
There's
B?
no cross product. There's no cross product. What are you talking about? You guys are reverting to a more primitive stage. You're going back to high school. This is like reverse
manually.
101.
The wedge product of A and
Count
B.
each box, find the area like that.
No, there's no boxes because there's no standard basis. So you don't know what vertical and horizontal means.
Just count the number of pixels on the screen and then add them up.
Okay.
You could do one thing.
Okay,
So
everyone
could,
now.
Say
please,
base times
quiet.
at this point.
You
Just
could
be
take
quiet.
the...
How do you mute everyone? It's out of control. Okay, so the answer is that there is no area of this parallelogram. The area is not defined. Okay? That is the answer. There is no area. If I give you two linearly independent vectors in a two-dimensional real vector space, they produce a parallelogram. There is a figure like the one I drew. There's nothing wrong in describing the set of points which make up this area, this region, but there is no area of it because we have no, the best thing that we could do is maybe to choose A and B as basis vectors. And then this thing you could say has area 1, but that's a useless concept because then any two linearly independent vectors would have area 1. Okay, so on the other hand, okay, so PAB does not have a well-defined area or volume. Okay. However, if we choose a basis E1, E2, oops. We can compare AB to E1, E2. So if I have a basis, let me just show you what I mean. If this is my basis now, E1, E2, then you can see that this thing will have an area, okay, in the sense that we declare that E1 P E1 E2 is equal to 1, the area unit area. Okay, and then we can see how many of these unit areas are going to fit inside this region. Okay, but we need the pixel. We need the unit area. If we do not have the unit area, we won't be able to measure the area of this thing. Okay, is that clear? Now, and we can compare the areas. Okay, and we're gonna see that in a minute. Okay, now a fact. I'm going to tell you now a fact about area. Okay, which, despite the fact that you spent years of your life thinking that you know what area is, I'm going to tell you that you actually we're not taught properly what the area of things is, because if I take so if E1, E2, if the area of the parallelogram of E1, E2 is equal to 1, then the area of the parallelogram of E2, E1 is equal to -1. Okay, this is something that people never told you about the area, which is that it has a sign. So what do I mean by that? So this square, it has a, it has a, the basic idea is that in order, if you have E2 and E1, right, in that order, then in order to compare it with the original, you need to flip the E1 and E2. So in a way, you could think of it this way, that if this E1, E2, if this thing had area 1, right, then you could imagine slowly exchanging the two vectors. You could imagine letting E2 move like this, and you could imagine letting E1 move like this, getting closer together. Okay, they will have a certain area. Okay. And then you could imagine so that they line up. And then you could imagine that they exchange direction. Okay, and then you could imagine that they are finally in their final positions like this. Okay, so it starts off being area 1. It starts to get smaller and smaller area gets to 0 area, and if you continue, it goes into the negative. Okay. So if you want the area to be continuous, right, if you want it to depend continuously on the vectors that you're considering, you're forced to go into the negatives. And so the way that we do this is that we say that area is an area of associated to a list of vectors. You need to give an order to the list in order to have an area. For the area to be continuous, it must take negative values. Not continuous, but like if you want it to be smoothly depending on vectors. You know, we don't want the area to do something like this, that we don't want the area to kind of have this behavior where it's as the vectors get closer and closer, right, the area drops and then goes to 0 and then suddenly becomes positive again. No, actually what you really want is that it continues. Okay, so what I'm going to do is define an area, or actually a volume. So this is a definition of what a volume is. A volume is a tool that measures volume. Okay, you could call it like a volume machine or something, but I just call it a volume. A volume on the n-dimensional vector space V is a map V cross V into the field I'll give this the name little v. And the number of these is exactly this dimension of v. So it takes n vectors and outputs the volume that's spanned by the, it gives the volume that is spanned by those n vectors. Okay, now notice that I'm talking about a volume, right? There's many different possible volumes because, like we said before, there is no canonical volume. There's no natural volume. You need to select a volume, and then you can use that volume to measure the volume of various different things. And if, you know, if there's a particular list of vectors that you want to consider to be the unit volume, then what you would be looking for is one of these volumes that would measure 1 for that particular list. Okay, and this has to satisfy such that the following conditions hold. So number 1, it must be linear in each argument separately. So why is that? Well, we know that if we have a box spanned by 3 vectors, let's say, and if you take one of those vectors and double it, the volume of the box should double, right? Each of the individual one-dimensional components, the volume should be linear. The dependence of the volume should be linear in each of the n input vectors. So this means, if I write it out, it means that if I have v of w1 up to w, let's say k minus 1, and then for the kth entry, we have, let's say, lambda w plus w prime, and then wk plus 1 all the way to wn. So if I just take the kth entry and put in a linear combination in there, then this should be lambda times the volume of w1 with w in the kth entry plus the volume that we get by putting w prime in the kth entry. And this is for all k. Okay, so it should be linear in each entry. Okay, and the second, so this is called, this, by the way, when something is linear in each argument separately, this is called multilinear. And the second property is that if at some point, let's see, how do I want to phrase this? There's different ways of phrasing this, but if any 2 inputs coincide, okay, so if you have 2 sides of the parallelepiped or parallelogram, and if the sides coincide, that means that this entire n-dimensional thing is actually flat. So it would be like having 2 edges that are parallel, and it gives you like a very, very thin, infinitely thin parallelogram. So if any two inputs coincide, V is equal to 0. Okay, now notice that the second property implies that if I take V of let's say if I take V plus W, let's see. Let's say that I have W1, and at some point I have Wi, and then if I, at some other point for I less than j, I get another Wj, and I continue all the way to Wn. Okay, so I measure the volume of this list of vectors. Okay, and so this thing is the same thing as V Wi plus Wj. So the reason that this is equal is because I added a Wj in here, but because Wj occurs twice, and because V is linear, right, this expression, this will be the sum of the two terms, one which includes V Wi and the other Wj, but the Wj term is going to have two Wjs, and that's going to mean that that term is 0. So the thing that I added is not going to affect the volume. And this is equal to the same thing, but okay, so now what I'm going to do is I'm going to try to do the same trick. I'm going to add Wi and up to Wn. So this is not a kosher move, because when I add Wi to this guy, to this entry, right, it's true that the Wi term will not contribute, but there will be a Wj term, right? So I need to subtract that out. Like this. So all I did here in this step was I added a Wi and I subtracted the Wi. So I did nothing. Plus, and then minus Wi. Okay, and then notice that we have the same thing occurring here. So this is 0. So this is equal to minus V W1 Wj Wi Wn. I kind of did this in a kind of unnecessarily complicated way, but I did it this way to prove a point. But anyway, you could think about this fact on your own. But the important thing here is that if you switch any two vectors, I, j, if you switch them so that they change places, we get a minus sign. Okay, so this volume, because of this fact, these two facts, I claim they are completely obvious from the behavior of volume. So if you were to write down the axioms of what volume satisfies, you would definitely write these two axioms. But I'm saying that this axiom implies that it is skew symmetric in the entries. If you switch the two entries, you get a minus sign. So this means that V 2 implies that V is skew symmetric in the n entries. It's sometimes called totally antisymmetric. Okay, so if you exchange, every time you flip any 2 entries, you get a minus sign. Okay, any questions about this?
Isaac, you have a question?
Yeah, I just want to make sure that like if you have a lambda in front of like the transformation V, it only goes to 1, right? Not like everything. Like for the first axiom.
Yeah, if you look at the first axiom, that's what you see, right? You see that if you have a lambda inside in one argument, that lambda comes out at the front. And of course, you can read the axiom the other way, which is what you're asking.
Yeah, so like basically you can put that lambda like into anywhere you want, right?
Correct.
Like
Correct.
in this.
Correct.
Yeah. And also I just a little bit confused about like can you move to the first axiom again? About like the plus thing, like if you just have like a one term that's like add to something, like but in fact like there's like a one term and the rest terms are the same, like the lambda w plus w prime thing.
Yes.
Okay, I just want to make sure. Yeah,
Yeah,
thanks.
I'm trying to check that it's linear in this argument, but it's actually linear in all the arguments for all k. You know, no matter which one you put a linear combination into, you're going to get a linear combination of numbers out.
Okay, yeah, thanks.
Okay, so now let's fix a basis. Okay, so that's what a volume is. You finally learned after so many years what a volume is. That is what a volume is. Okay. So now let's choose a basis, E1 up to En, and a volume, V. So V of E1 En is equal to what? Well, we don't know because there's many potential volumes, and we don't know which one. So all we know is that we have a volume, and so this will give me some number in the field. Okay. So now that we know the volume of the basis, let's figure out the volume of an arbitrary list of n vectors. So let's take vectors x1, x2, all the way to xn. Okay, and let's now compute the volume of x1, x2, xn. Okay, so we have all of the information that we need to compute this volume because we know that the volume is multilinear. And we know that when, whenever you have a repetition, whenever you have the same vector and 2 entries, the volume is 0. So we can just expand this out. So what will this be? So this is going to be V of, x11, E1. Right? We just need to plug in all of these things and then expand. Okay, so what will we get? Okay, so So the first term that we're going to get is x11, so v x11 e1. Okay, now what will be the first contribution in the second argument, right? I could put x21 e1, but I know that this term will be 0 because I have a repetition of e1. So this one will not contribute. The next one will be x21 e2, sorry, x22 e2. Okay, and then if I put here x31 e1, x32 e2 plus x33 e3, you see that this one will not contribute because there's an e1 already in the first argument. This one will not contribute because there's an e2 already in the second argument, and I don't want any repetitions. So the first term that is going to contribute is the e3 term. So I'm going to get x33 e3. And we're going to continue this way until xnn en. Okay. And then the next term is going to be, let's say that we pick the same choices until x, let's say at xn minus 1 stage. Okay. Instead of picking the n minus first term, I'm going to take the nth term, which will be en. So I basically choose the very first vector that I can for all of these. And then right before the end, I decide to skip over the term that I already wrote here. Right? And so then in the next stage, this is going to be x. I can't put xnn en because there's already an en. So I need to put xnn minus 1 en minus 1. And I'm going to have a whole bunch of terms. So let me write the result of this. So I'm going to use linearity. So, okay, how many terms am I going to have, first of all? So, whenever you choose a basis vector, one of the components, right? Once you choose one of these components to put in the first slot, then the first component is basically excluded from any other slot because it will just give 0. So that means that when I choose E1, I'm not allowed to select E1 from any of the remaining. If I choose En, right, then I cannot choose En for the remaining terms. They will all contribute 0. So basically, I'm allowed to choose each one of them once. I can choose E2 here, E1, E3, E5, E7, right? As long as I only choose one term from each of the n vectors, and as long as all the terms are distinct, they will give you a non-zero contribution, a potentially non-zero contribution. So the easiest way to do that is just go down the diagonal, take the E1 term from X1, E2 from X2, E3 from X3, and that's what I did here. But what you could do is you could apply any permutation of the n first numbers, 1 to n. You could apply any permutation and you could get that, right? So there are as many terms as permutations of 1 up to n. Okay, and notice that here, this is the permutation n minus 1 n. This is the transposition. Okay, so if you work all of this out, what will you get? So the first term will be x11, x22. I'm using linearity now in each argument separately. xnn times the volume of E1, E2, E3, En. The next term will be x11, x22, all the way to xn minus 1 n, and then I do xn n minus 1 times the volume of E1, E2, up to en minus 2, and then I have en here, and then en minus 1. And I'm going to have a whole bunch of terms like this. Okay, now notice that here, the difference between this term, this is en minus 1, en. Here they're all in order, and here the order is switched. So what I could do is I could switch it to make this term look exactly like this term at the cost of a minus sign. So what you could do is do the switch, and you can change the sign. Okay, these two are together. So you change the sign and switch. Okay. And so what you end up with is that the volume of the basis comes out in front. So we get C times a big sum. And the sum looks like this: x11, x22, up to xnn, minus x11, x22, xn minus 1n, xn n minus 1, plus minus, okay, there's a whole bunch of terms, all with pluses and minuses. And the idea is that what you need to do is, let's see, for 3, there would be permutations, 6 of them. So let me copy this. Okay, so the first term would be to choose the first term, the second term, and the third term. That's what gives this term. The second term involves the first term, the last term, and the second term. Okay, but there are other possibilities of choosing. You could choose the second, the first, and the third, the second, the third, and the first, the third, the first, and the second, and the third, the second, and the first. So that means that there will be, and this here, what I'm drawing here is just this picture. I'm drawing the n components of each of the n vectors. If I take this component, this component, this component, and plug that into the volume, I will get this term times c. If I plug this, I'll get this term times c, but with it will have a minus. Okay, and so this term, yeah, so in the end, what you get is c times an expression that looks like this. This is how it's usually written. You take a sum over the elements of the symmetric group, the permutations on n permutations of the set 1 up to n. And then what you do is you take from the first vector, you take sigma of 1. That's the component you take. From the second vector, you take sigma of 2. And from the last vector, you take sigma of n. Okay, and then you need to multiply this by a sign. Oops. You need to multiply by the sign of the permutation. And this sign is computed by expressing sigma as a product of transpositions, ij, and it's minus 1 to the k. Okay, so if it requires k transpositions, you're going to get k minus signs because of the behavior of the volume. Okay, this quantity is called the determinant. So basically the The determinant is basically telling you, so to conclude, the determinant so the volume, the conclusion is like this. The volume of x1, xn divided by the volume of E1, En is equal to the determinant of this matrix, x11. Okay, so there is an intimate relationship between the determinant and volume, and this is what it is. There is such a thing as a volume. It's a multilinear function on a vector space, which satisfies the fact that it's 0 on repetitions. It's a totally anti-symmetric multilinear function on a vector space. And that thing, when I change from a basis to some other list, the ratio of the volumes is given by this polynomial function of the entries. And the polynomial is basically the sum of the products of n matrix entries, no two of which lie in the same row or column, with appropriate signs. Okay, so we're going to say more about this next week, but I just wanted to introduce it properly. Okay, let's go to questions. We have office hours now, so I'll let it merge into office hours. I'm just going to get some water. I'll be right back. Okay, yeah. There's got to be some questions, so I'll just wait.
So there was a request by Sina in the chat. If Sina, you want to ask?
Where is Sina? I don't see him.
Okay. So, all right. So what Sina's request was if we could do a concrete example, I'm presuming referring to determinants.
Yeah, I mean, we're going to do more on determinants next week, like I said, but let's take a look. So basically this is, if you look at this formula, it's basically giving you a recipe for determining a volume, right? So if we take, let's say we work in Rn, okay, with the standard basis. Okay, and let's, so actually this is also giving a kind of, let me just make a corollary of this. Corollary is that there is only one volume up to scale. This is a very important result, but you see what I mean, that the volume of a list of n vectors is this particular determinant multiplied by this number. So if we know what the volume of a particular basis is, then every volume is going to be given by this determinant function times that number. Right? So it's basically saying that, so let's kind of use this. Rn is a standard basis, and let's let V be the volume such that V of E1 up to En is equal to 1. So we declare that this standard basis has volume 1. And that's good because we know that the unit cube in n-dimensional Euclidean space should have volume 1. Okay, but the nice thing then is that the volume of any list of vectors is simply given by the determinant. Okay, so let's do an example. So let's do for R2, let's check that it agrees with our previous definition of the determinant. So if we have, let's say x1 is AB, and say x2 is CD, then this is AE1 plus BE2, and this is CE1 plus DE2. And so the determinant of x1, x2 will be a sum over elements of S2. I'm going to write it kind of in the formal way so that you understand how to kind of unpack the formula. Let me give these. Let me give you different numbers. So I'll call this x11, x12, x2.
We were here over 20 minutes ago.
Okay, and then we should have -1 to the sine of sigma times x1 sigma 1 times x2 sigma 2. So let's break this out. So there's two, S2 consists of two, there's the unit, I mean the identity element of the group, and then there's the transposition 1, 2, which switches 1 and 2. Okay, and the sine of 1 is equal to 1, and the sine, is equal to 0, and the sine of 1, 2 is equal to 1. It's basically counting the number of transpositions needed to write the element. Okay, and then so the first element is going to be -1 to the 0 times x11, x22 plus -1 to the sine of 1, 2 times x12, x21. So I get x11, x22 minus x12, x21, which is indeed, AD minus BC, if the matrix was like this. Okay. Let me do just one more example. So if we had x11, x12, x13, okay, then we would have, sometimes determinant is denoted by putting these straight lines on the side. But I prefer to just write it just so that there's no confusion. The determinant of this list of vectors, right, is going to be a sum. So you could think of it like this, that every permutation is going to pick, the identity permutation is just going to take x1, it's going to take 1 to 1, 2 to 2, and 3 to 3. But you can also have x1, 1, x2 to 3, x3 to 2. So that's the transposition 2, 3. This is the unit. This is 2, 3. Then there's x, if I write it, actually maybe it'll be useful to write it carefully. One second. So the elements of S3 are like this. Like this. So, and the signs, oh yeah, sorry, let me make some space between them. So this one is sign 0. There's 0 permutation transpositions. Here there's 1 transposition. Here's 1. Here's also 1. And this one, if you look, you could first exchange 1 and 2. So this one is, and then you can exchange 2 and 3. Oh no, I got it the wrong way. First do this, and then do this. Okay, so there's 2 transpositions. So this means that the sign of this would be 0 again. Or if you want, you could put it to be 2, but it's only the parity that matters because I'm taking -1 to the power. So so this one is still 0, and this one is also 0. So then what I'm going to get is x, 1 is sent to 1, 2 is sent to 2, 3 is sent to 3. Then I'll get a minus, 1 is sent to 1, 2 is sent to 3, 3 is sent to 2. Then there's another minus, x1 is sent to 2, 2 is sent to 1, 3 is sent to 3. x1 is sent to 2, 2 is sent to 3, 3 is sent to 1. There's a minus, x1 is sent to 3, 2 is sent to 2, and 3 is sent to 1. And then plus x1 is sent to 3, 2 is sent to 1, and 3 is sent to 2. Okay, so, I mean, in a sense, it's extremely tedious, but I mean, what does it really mean tedious if you're not really doing it? If you're getting a computer to do it, it's not tedious. But anyway, the determinant is defined this way, and it allows you to do, this literally will give you the volume of any 3 vectors in 3-dimensional space. This bizarre formula, this is the formula for the volume of x1, x2, x3. The parallelepiped, that's an ancient word. You have 3, x1, x2, x3, and these things form a box. Okay, so the volume of this box is given by this expression. Okay, so and of course the box is not, is not the unit box, or is not perfectly horizontal and straight. It's made of 3 arbitrary vectors. Does that answer your question?
Yes, that
your
answers.
response?
Thank you.
I was answering Sina's question. Did he get it?
Yeah, my name changed, but yeah, for some reason I am Sina now.
Oh, I see. Okay.
I'm actually Daniel, but
Okay. Yeah. So yeah, if you, I mean, without making a big deal out of it, we have managed to define volumes for arbitrary dimensions. So in particular, if you wanted to do 4-dimensional volumes, this gives you the right formalism to do that.
Okay, so Omar has a question.
Hello, Professor.
Hi.
Yeah, so we know that the determinant of a 2x2 matrix implies linear dependence. When it's equal to 0, implies linear dependency in the list of
Yes.
2x2.
Yes.
And so we'll have to prove this for the general case of determinants as well, or?
Yeah, that's right. So it's very intuitive, when you say that, if the determinant of a list of vectors, or rather, yeah, I mean, you have to be careful. I'm going to say more about determinants next week, but it's not quite right to say that it's determinant of a list of vectors, because you kind of need to be able to expand that list of vectors in terms of a basis. So it's really the following. It's like saying, if you have a volume, so the claim is this, is that if V is a non-zero volume and V, the volume of these n vectors, is equal to 0, then the list is linearly dependent. Yeah. So and in particular, if you're working in Rn and you're using this particular volume, the volume that's determined by the standard basis, then this is, let's say, V standard. The standard volume would be the one for which the unit square, the unit cube, has volume 1. And if this standard volume of a list of vectors is equal to 0, then the list is linearly dependent. That is a true fact. It's not so difficult to prove. Based on what we're going to do on Tuesday, it'll be completely obvious. So I'll just wait until Tuesday. Yeah.
Sure.
Basically, what we want to do is we just want to study how volumes are affected by linear transformations, and then it'll be clear that that what you said, your conjecture holds. Omar's conjecture will be true on Tuesday.
All right then. Thank you, Professor. Have a nice weekend.
You too. Have a nice weekend. So take a look at the assignment so that if you have questions, you can ask me now, because it's your chance. Or if you have questions about the Jordan canonical form, but you guys are probably extremely tired with the term, so you're probably just you probably don't even know what you're doing anymore. You're just doing too much, probably.
Professor, I have a question on the application of the Jordan canonical form.
Yeah, go ahead.
I was reading Michael Arton's algebra book, and in his chapter, he defined multiplication of matrices split into blocks. So if you have a Jordan canonical form of two matrices, and for some reason their blocks agree, do you like one of their blocks agree? Can you just speed up multiplication of those two matrices? Like I don't know, maybe I'm just confusing myself. Like, is there a connection between multiplying two matrices in Jordan block form that can be used to?
Well, okay, those are two separate ideas. I mean, I don't think that Jordan blocks are particularly, you know, what you're talking about is the idea that, well, okay, so what you're talking about is the idea that you could have matrices which are broken up into these blocks. And that if you, let's say, to make things simple, suppose that this is an n by n matrix, and then we have another n by n matrix, and it has, we divide the matrices into the same size blocks. So this is, let's say, k by k, and this is also k by k. So the kind of the simple-minded way of thinking about it is that when you multiply this matrix against this one, you know, if you, there's a kind of natural kind of question that might occur to you, which is, you know, is there a way for me to ignore the details of what is going on in these four pieces? Okay, and let's look at the answer. The answer is going to be another n by n matrix, and I can divide that one to the same k by k block, and so on. So the question is, you know, can I express this block in terms of the blocks here, rather than to give you a formula for every single entry in the answer, which is what we normally do. We normally say that, you know, the ij entry is the ith row and the jth column dot product together, and we get this number. But instead of giving you that type of description, can you describe this block as a combination of these blocks? And you can kind of see what's going on. You can kind of see that this k by k block, so this is k by k, and this is k by n minus k, and this is n minus k times k, and this is n minus k times n minus k. Okay, and you can kind of see that when you multiply this through, this k by k and this k by k will be multiplied together. You could imagine, you know, how do I obtain these entries? I have to multiply this row by this column, this row by this column, and so on. So inside there will be this k by k multiplied by this k by k, and that will take care of this part of the first row multiplied by this part of the first column. When I multiply this block by this block, I will be considering this dot this. But I still have this dot this. So in other words, let me give these names. So I'll call this A, B, let me just call these I'll call this A1, sorry, A11, A12, A21, A22, and this one B11, B12, B21, and B22. So these are the blocks. And notice that it makes sense to multiply A11 times B11, and that will give you a K by K matrix. But that will not contain, that will not be correct for what this upper block is, because as I said, that will only contain this part of the first row multiplied by this part of the first column. We also need this times this. And so that means that A12 multiplied by B21 must be the rest of the contribution. Okay, and similarly, we do A11, B12 plus A12, B22, and similarly for the others. Okay, so when you look at this, there's a couple of things to notice. So first of all, it looks exactly like normal matrix multiplication, where if these were scalars, if this was a 2 by 2 matrix, this is exactly what the formula would be, right? A1, B, this times this plus this times this. That's what we get here. So the formula looks exactly like normal matrix multiplication. But the thing you need to be careful of is that, in here, this multiplication is a matrix multiplication and it is not commutative. So the order in which the formula is written is very important. If this was just a scalar, then I could just write, AB plus BA. It doesn't really matter. But here the order is important in this formula for block matrix multiplication. Okay, so getting back to your question, I don't know who asked the question actually.
Daniel Asina.
Oh, okay. Because for some reason it's not, usually what it does is it shows me who's asking, but for some reason it doesn't want to do that. Anyway, so of course Jordan blocks will be in this format, and it'll be even simpler because you won't have this A12 and A21, and so it'll be very simple to multiply matrices. But that's not the purpose of Jordan blocks. The purpose of Jordan decomposition is that, Jordan decomposition is that two operators, T1 and T2, are equivalent. Sometimes they call it similar or conjugate, if and only if the Jordan form of T1 is the same as the Jordan form of T2. In other words, the Jordan canonical form classifies your operator. So if you want to know whether your operator and someone else's operator are the same operator, just written in different bases, what you need to do is compute the Jordan canonical form of both and compare and just look at, see if they're the same.
Okay, yeah. I guess my question just didn't make any sense because I just heard the word blocks in Jordan form and I was like, block multiplication.
They're the same word. You're right.
Yeah.
It's the same thing. So I just explained both things separately.
Yeah. Yeah. So that really helps. Thank you.
Okay. You're welcome.
All right. So Diba has a question.
Yeah, I just want to know why we can't take the determinant of non-square matrices, or can we?
Okay, determinant is, the whole purpose of today's lecture was that the determinant is intimately related to volume. Okay, and so in order to have a volume in an n-dimensional space, you need to provide n vectors. If you provide 2 vectors, you're not getting a volume, you're getting an area of something flat in that dimension. Okay, so the way I think about it is like this, that if you give me n vectors in n-dimensional space and you expand them out in terms of a basis, you're going to get an n by n matrix. So n vectors in n space gives you an n dimensional, gives you an n by n matrix, and the determinant of that matrix gives you the volume. Okay, so if you give me an n by k matrix, if I give you a 3 by 2 matrix, okay, you could think of that as 3 vectors in 2 space, or you could think of that as 2 vectors in 3 space, right? In either case, you're not going to get you're not going to get a volume, right? So volume is not the correct idea, it's not the correct concept, and determinant is not the right concept. However, it doesn't mean that there's not something else that is important. So, for example, if I give you two vectors, well, in 3-dimensional space, they will give you a kind of 2-dimensional figure inside there. And so I might want to know, some kind of area-like thing of that, okay? And so the question is, what is the, what is the key property that a list of vectors inside n-dimensional space has? Okay, and the reason, so the answer to that question is that, okay, you're right, it has an area, but it has more than area, because, if I take these 2 vectors, right, let's say if I take these 2 vectors, or if I shear this over with the same height, okay, I'll get another area, but they have the same area, right? So if all I was measuring was area, then these 2 vectors and a sheared version of them should have the same area. I think we would all agree on that. Okay, but these 2 vectors could also be embedded in this way. It could be embedded in a different way in 3 dimensions. And so this area and this area, okay, if you were only paying attention to 2-dimensional area, they would be the same, okay? But the replacement for volume in n-dimensional space is something that actually keeps track of where the 2 vectors actually are, like how they're inclined in 3 space, okay? So there is a version of the determinant for less than n vectors in n-dimensional space. Like you could say for 2 vectors in 3 space, or for 2 vectors in 4 space. There is a notion of determinant. It's a determinant-like thing, but that determinant-like thing is not a number. It's not a scalar quantity. It's a vector quantity. There is a vector space of these volumes. These, I don't know what to call them. You could call them. You could call them like.
Pseudo volumes.
Yeah, that's right. Subvolume or a K volume. This notion of K volume is not going to be a map, a multilinear map into the field. It's not just a number. It is. It has a value in a vector space, which we have to define, and that vector space is called the kth exterior power of V. Okay, and that's where these subvolumes lie, and so the idea is actually, I mean, I'll talk about it hopefully next week, but the basic idea is, if I give you two vectors in 3 space, right? If this is X and this is Y, okay, then it's not true that you do not have a volume, which is a number, but you have a wedge product, which will be made of the component 2 by 2 determinants. So you'll have like AE minus BD, AF minus CD, and BF minus CE. Okay, roughly speaking. So we'll do this more precisely next week. But it's a quantity that has a vector nature. It has 3 components, and these 3 components, they tell you about the area, but the area is it's a kind of directed area. It's an area in a particular direction, which volume doesn't have. Volume does not have direction. It has only scalar nature. So yeah, this may seem familiar to people who know the cross product. So the cross product is an example of this procedure, but it exists in any dimension. And the point is that in higher dimension, the number of components grows a lot faster. So if you were in dimension 4, this wedge product would have 6 components rather than 4 components. Just because in 4 dimensions, there's many ways for a 2-plane to be oriented. It's not just a single direction in 4-dimensional space, because there's 2 vectors. Each of them can move around. And so it's like 4 choose 2. So it's like 6. The 2 vectors can move kind of in many ways. So it's a 6-dimensional space of areas in dimension 4.
Okay. So this vector is not in whatever.
It's not in the vector space that you are looking in where the vectors are. It's a larger vector space, which is large enough to handle the amount of information that is contained in a pair of vectors.
Oh, wait. So in a sense, like the more information you're given, if you're given enough vectors that you have n vectors in an n-dimensional space, you can express their volume in kind of a simple quantity, just as a scalar in the field.
Yeah.
But if information is removed, suddenly you need a larger space. Almost.
Yeah, that may seem counterintuitive, but the point is that these volumes, they have a because of the fact that they're multilinear, what it means is that what it means is that if you give me n vectors to give the volume, right? You're saying that you're giving me a lot of information because you're giving me n vectors. But actually, if I add one of these vectors to one of the other ones, if I move this one, let's say, over, right? So for example, if I take the volume, of E1, E2, E3, this is going to be the same as E1 plus E2, E2, E3. Okay, because of the fact that this is a repetition and it doesn't add anything to this expression, right? So what I'm trying to say is that the volume forgets a lot of information that is contained in the list. In addition to using that information, it also forgets some information. It does not care about the particular 3 vectors that you picked. You could rearrange them in many different ways. Okay, so it's true that you're providing me a lot more information, but that information is highly redundant in dimension n for n vectors. If you give me only 2 vectors, you're giving me less information, but there's less redundancy as well.
Mm-hmm.
So in fact, you're giving me more information if you give me 3 vectors than if you give me 5 vectors in 5 dimensions. You're actually giving me more information if you give me 3 vectors. And what I mean is you're giving me more information from the point of view of this volume, because the volume, it doesn't care about all the data, right? It combines it into this form, right? So it takes the input data, it processes it in a certain way that loses information. And the higher the number of vectors, the more information it loses. So that's kind of what's happening. That's the reason why you have this apparent contradiction.
Oh, thank you.
You're welcome. Everyone is trying to think of more and more difficult questions. That's good.
I actually have no idea what we're discussing at the moment. So
say again? You have no idea about which?
Like I'm actually having a hard time getting my mind over these concepts. Like
Well, I mean, I'm talking
understanding
about
what's going
something
on.
that I'm giving a preview, so don't worry about this wedge product. But the thing that's important is the volume. That's the important thing. So try to make sure that you understand what a volume is. We have to axiomatize it. Just because, I started the lecture by explaining to you that there is not a God-given volume on a vector space. You need to choose one. But then you need to know what it is. So that's what it is. It takes n inputs, it's multilinear, and it's 0 on repetitions. And this gives you a formula. This is just a standard formula for a volume on Rn. So we see this is the generalization of the simple formula, AD minus BC. This generalizes to this sum over permutations. Let me check if there's anything in the chat. Is there anything?
No questions in the chat.
No important questions in the chat.
Yeah, no important ones.
And this idea that the volume has a sign, that's also very important. Maybe I'll just mention that the sign of the volume is known as an orientation. So if you choose a volume on a vector space, you basically, so the volume, let's say that we were in Rn. One of the volumes on Rn, the standard one, is the determinant of the matrix that we get. By writing all these vectors. But any other volume will be a constant multiple of the standard one. Okay, where this can be anything in R. So that means that that you have a choice. Here's the standard volume. Okay, but there are many other possible volumes that you could pick, which are all scalar multiples of the standard one. And they separate into two different classes. The class that's on one side of 0 and the ones that are on the other side of 0. And these classes are, what we say is that if two volumes are in the same class, then they determine the same orientation on V. These two types of volumes are called orientations. So when you choose a volume, and you can choose any like positive number multiplied by the number, multiplied by the volume. So if any positive multiple of a volume determines an orientation, what is called an orientation. And there's two different orientations. It's like on a sheet of paper, there's two sides, right? The two sides, if you flip something over, you change its orientation. And similarly here, there's a notion of orientation in n-dimensional space, which is somehow flipping over the whole space in a sense, considering a different volume, an opposite volume, a volume in which the unit cube has volume negative rather than positive. That would be a different orientation on the same space. I'm just deliberately trying to confuse you.
Emily, you have a question?
So I just want to confirm something with the part where like we switch to standard bases and then the change sign part. So like basically you can pick any of the E1, E2, and then you can switch it and the signs will always change with, because since it's plus, it can always change. You can just pick any one of the E1, E2, all the way to like EN.
The only thing I can tell from your question is that you're confused about the signs. But should I just explain the signs, or do you have like an actual more specific question?
You can just, because in this specific example, we're switching only like EN and EN minus 1. So we can also switch like E1 and E2. And all
that's right. That's right. Yeah. Okay. You could make any switches you want. Yeah. Okay. And?
Okay. Oh, in the beginning, I was just kind of confused. Yeah, I think I get it, because in the beginning, we determined that like, because when you switch, they have opposite signs.
Yeah, exactly. So if I have something like this, let's say I have suppose I have like this, A11. Suppose I just had this example where I just have, I don't have everything. Like I didn't make it the most general possible. I just cut it off here. This only has 1 and this only has 2. This has 3 terms, but it's okay. This is just an example of computing a volume. So what you would get is you would get one term, which is this, this, and this. When I expand this out, use these sums, right? I'm going to get this first term. The second term is going to be like this term, and this term. Okay. The third term is going to be like this, and this. That would be 3, and so on. There's going to be many terms. So let's just write the first term. It's going to be A11 comes out, A21 comes out, and A32 comes out. And then I have V, E1, E1. Oh, I'm sorry. I wanted this to be E2. E1, E2, E2. That's the first term. But there's a repetition here, so this term goes away. The second term also has, the second term doesn't have a repetition. So this will have A11, A21, A33 times V of E1, E2, E3. Actually, I wanted, it's okay. Let me do it again. I just pick the worst possible example. Okay, so when I compute the volume, I'm going to get a term that involves this. Sorry, I thought I had written them all. And this. This will be the first term. What will be the second term? If I do it in alphabetical order, let's say, I'll start with E1, and then I'll go to E3, and then I'll go to E2. That will be the second term. So when I work the first term, I get A11, A22, A33, V, E1, E2, E3. Then the next term, A11, A23, A32, V, E1, E3, E2. Let me do one more term. So I got the two terms that will go with E1. Let me do an E2 now. E2, that will hit E1 and E3. Okay, the third term will be A12, A21, A33, V, E2, E1, E3. Do you see, I'm just expanding it out using the linearity. It's linear in each argument. So I'm going to get, like, how many possible terms would there be? Well, there would be 3 times 3 times 3 terms. But the ones that involve repetitions are all 0. So there's very few terms in the end. I just wrote 3 of them. But look at what the result is. So all of the signs are plus, because I just had pluses here, plus, 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 plus. These are all plus. Okay, but each one of these is multiplied by V, E1, E2, E3, but this is not E1, E2, E3, right? So I want to take this volume out of the sum. So I want to write this as V, E1, E2, E3 times, a bunch of terms. Okay, so if I need to take this out here, I cannot take it out here. It's wrong. They're not the same. Right? So instead, what I need to do is I need to use the property that I can switch 2 and 3. And this will be equal to minus V, E1, E2, E3. Okay, and so that means that I can put here A11, A22, A33. And then the next term will be with a minus A11, A23, A32. Okay, and then for this one, I need to switch these two. So that's one switch. And so I'm going to get a sign, which also is minus A12, A21, A33. Okay, but there will be other terms. There's going to be a term that looks like this, V, E2, E3, E1, which comes from, let me draw it in pink. So E2, E3, E1. That will be term 4, let's say. Okay, and what am I going to get? I'll get A12, A23, and A31. Okay, and then I need to kind of put a term in here. And what you see is that how many switches do I need to put it back into the proper form? So if I switch E1 and E2, then I'll get V, E1, E3, E2. And I'm still not in the right format, so I need to switch these two. So there's a second switch to get it to V, E1, E2, E3. So there's a -1 from that, and there's a -1 from that. So in total, it's a plus.
Okay. You just basically use the properties and you
Yeah,
can just
you just use the
compute.
property and just expand it out. It's no big deal. Yeah. That explains why the determinant has this funny formula, which involves the sign of the permutation and you sum over all possible permutations. It's just an explanation for why this sign is there.
Okay, yeah. Thank you.
You're welcome. Okay, everyone. Is there an emergency question, Shizuo?
I noticed that the which product of x and y and I noticed that this form is similar to the formula of curl. So is there any relationship between this?
Yeah. So what you said was that the wedge product of two vectors in three-dimensional space has a formula which looks exactly like the one for the vector cross product. Okay, so it is true that they are almost the same operation, but that is only true in dimension 3. So in any dimension, there's a wedge product, but it will be quite different in higher dimensions. So for example, if you take two vectors in 4-dimensional space, okay, and if you take their wedge product, you will not get another vector in 4-dimensional space. So it does not behave like the cross product. It will be a vector in a 6-dimensional space. So we need to get to that next week. So the basic idea is that there is a version of the cross product in other dimensions, but the problem is that it is not a product on the vector space itself. It's a product that takes two vectors and outputs what's called a bivector. And this bivector is a vector in a larger vector space, which is not the same as the vector space you started with.
Okay, thank you.
You're welcome. Okay, everyone, have a good weekend. See you on Tuesday. Good luck with the assignment.
See you.
Bye-bye.